Okay, so the last lesson for this unit is about applications, for exponential growth and decay. So we know what growth and decay are. Growth is when you are growing by a set percentage every period, whereas decay is when you are decreasing by a percentage every period. Again, let's not worry so much about this. I want to go over more similarly to the way I taught it before, so don't worry too much about that. Now, the thing to understand about, let's write the equation the way we saw it before. N of t is NO 1 plus r to the power of t over d, right? And I said d was the, let's just review what all of this means. N of t is the current amount at time t. T equals the current time, so whatever, 6 days later, 20 years later, whatever. NO is the initial amount, so whatever you started with, or what was there at time 0. R equals the growth rate in, so the growth rate as a decimal, right, as a decimal. So for example, 4% growth equals 1 plus 0.04, right? The 1 plus r would be 1 plus 0.04. Finally, d is the compounding time, or the growth period. So does it grow every day, every year, every 3 days, etc., right? So if this is different than the unit t is measured in, we have to be careful. If it's not different, then we can just ignore it. So here, let's just go through these ones as an example. This one is definitely going to be growth. The reason is because 1 plus r is bigger than 1, right? If you go back to an exponential equation, you'll remember that you always have growth if b is bigger than 1, and decay if b is less than 1, right? So you have 1.04 here. 1.04 is bigger than 1, so you have growth. Here you'd have decay, right? Because 1 plus r is less than 1. The initial value here is 15, whereas here it's 500. And the growth rate here is 4% per period, whereas this is 15% per period. And again, where am I getting that? 0.85 is 1 minus 0.15, and the 0.15 would be the r, right? It's a negative because it's decay. Okay, so that's where that 15% is coming from. Okay, so it says an antique vase was purchased in the year 2000 for $8,000. The vase appreciates in value 6% per year. What is the estimated value in the year 2040 to the nearest $1,000? Okay, so t equals time in years. D equals growth period, which in this case is per year. So what we could say is D is equal to 1. We don't really need to worry about D because it's measured in the same unit that T is measured in. And O is the initial value of the vase, which was $8,000. And the rate is 0.06 because 6% is 0.06. T is, I'm going to say time in years since 2000, right? Because 2000 was when we started measuring it. Okay, so N of t would be equal to NO 1 plus r to the power of t over d. And if we just fill in what we know here, we would get that this is NT is 8,000, 1.06 to the power of t, because we don't need a d, and the growth rate was 6%. So it says, what is the estimated value in the year 2040? Okay, so the year 2040 is 40 years after 2000. Therefore, t is equal to 40. So what we're looking for is n of 40. And we do 8,000 times 1.06 to the power of 40. Now, probably you're not going to get this right if you guess how much this thing will be worth, right? You think to yourself, okay, the vase is going up by 6% per year. How much would it be worth 40 years later? I mean, 6 times 40 is 240%, so I don't know, maybe $20,000 or something like that. Let's see. N of 40. Let's calculate it. Let's draw it actually. Okay, so let's draw it here. So NO is 8,000, R is 0.06, N of T is NO times 1 plus R to the power of X. Sorry, not T. I gotta put X in GeoGebra. Okay, so how much is this thing worth? So you can see at time 0, it's worth $8,000. And where is it 10 years later? Okay, 10 years later, it's at $14,000. 20 years later, it's at $25,000. 30 years later, it's at $45,000. And the question we were asked, which is how much was it worth 40 years later, is $82,000. 10 times its value, right? Interesting how these things work. It doesn't seem like 6% is such a big deal, right? And yet 6% growth over a 40-year period is an extreme increase in value, right? Okay, anyway, N of 40 we said was 8228574. And we had to round to the nearest thousand, so N of 40 is 82,000. Okay, so that would be our answer. The nearest is 82,000. Okay, yeah, we already know that. All right, this time. A car depreciates, right? So often pieces of art or investments or houses tend to go up in value. Cars tend to go down in value. So this one, we're talking about a car that depreciates at 15% per year. You buy the car at 15,000, find the value of the car in 3 years. Again, N of T is going to be NO, 1 plus R to the power of T. We don't need a D here because it's per year. It depreciates per year, and time is measured in years. So we don't need a special value for D. We're just going to leave it as T. Now 15% depreciation means it's going down by that amount, means our R is equal to negative 0.15. So, and our NO is obviously whatever the car was worth when we bought it, which was 15,000. So when we plug in the equation, we get the value of the car is equal to 15,000, 1 plus negative 0.15 to the power of T. And we can really just sort of make that look a little easier if you go 15,000, 0.85 to the T. Okay, so this is something that's going to lose 15% of its value every year. Again, all you have to do to answer the question is plug in 3 and see what you get. But let's graph it again so we can have a look at this. So let's change NO to 15,000. And we'll change R to negative 0.15. So our $15,000 car, 40 years later, is worth 22 bucks. Now, again, is this model that useful for a car that's 40 years old? I mean, maybe. A car that's 40 years old is probably only good for scrap metal. Whether the model's really that useful beyond a certain number, maybe it isn't, but it seems pretty solid for the beginning. And notice that the car loses a vast amount of its value in the first 10 years. Like, it goes from 15,000 to 3,000 in 10 years. And then in the next 10 years, it drops from 3,000 to 600. It doesn't seem like as big a drop, although it's dropping at the same exponential rate. In any case, they wanted us to know what it would be worth at 3, so let's do 3 and N of 3. 3 years later, your $15,000 car is worth $9,211. And 88 cents. Okay, so the car would only be worth $9,000 after 3 years. Okay, a type of bacteria Yeah, so again, just ignore this. This is the way I taught it the first time. Sorry, I'm not going to delete it, but we're not going to fill it out. Okay, because we already know how to do this. A type of bacteria culture doubles in size every 15 minutes. Okay, so let's make some commentary here. NT, same equation. NT is NO 1 plus R to the power of T over D. Oops. Okay, now let's write down what we know. The growth rate equals doubling. Now you may remember from earlier in this unit, when something is doubling, it is growing at 100%. So R is equal to 1. Okay? If you have $5 and you gain 100% of your money, you gain another $5. You doubled it. Right? So 100% growth is doubling. So, and it says it doubles every 15 minutes. And how many are in the culture 1 hour later? Now, this question has two complicating issues. Number one, it has a doubling time. Number two, it's measured in terms of hours. Okay? So, your D has to be measured in the same unit as T. Must be in the same unit as T. So here are my options. Okay? I can either let T be in minutes, in which case D is 15, or T is in hours, I could say, and therefore D is 0.25, because remember, 15 minutes is 1/4 of an hour. Let's do it both ways, and you can just see, why both of these things work. So we'll just split the solution into two boxes here. So let's do it first in minutes, and then we'll do it again in hours. So in minutes, my equation would look like this. N of T is equal to 100 bacteria, 1 plus 1 to the power of T over 15. Okay? Now, my question says, how many bacteria are in the culture 1 hour later? If I'm measuring that in minutes, I would want to plug in N of 60, because 60 minutes is 1 hour, right? So in the minutes solution, T is going to be equal to 60. What do I get here? I get 100 times 2 to the power of 60 over 15, which is 100 times 2 to the power of 4, which is 100 times 16, which is 1600. Okay, so N of 60, 1600. So therefore, 1 hour later, there are 1600 bacteria. Okay, let's do it in hours this time. In hours, T is going to be equal to 1, and D is going to be equal to 0.25. So let's go back over here, and we'll just add that. D is equal to 15. Now in hours, we should get the same answer. Let's investigate. 100, 1 plus 1 to the power of 1 hour over 0.25, right? Because 0.25 is our doubling time now. So N of 1 is what we're looking for. Is equal to 100 times 2 to the power of 4. And from here, you can see it's the same answer. Okay? So it is your choice in these questions whether you want to use minutes or hours, or days or years or months or whatever, like whatever's appropriate. But the rule is whatever T is measured in, D also has to be measured in that unit. So either T and D are both measured in minutes, or T and D are both measured in hours. Either one works. Depending on the question, you can decide which one is easier. Okay? Let's try another one here. So this is a phenomenon called half-life. And I don't know if you've studied this in science, but things that are radioactive decay and become less radioactive over time, or I should say become different. Some of them become different radioactive things. But so as the substance decays, it takes a certain amount of time for it to lose half of its radioactive section, right, or its radioactive material. So if you were to graph this, right, let's just graph this for a sec. Let's imagine we started off, let's just make it really simple. Let's say we have a substance where we have 100 grams of whatever and currently. And we know that in 5 years' time, it will be split in half. So in 10 years' time, it'll be split in half again. In another 5 years after that, it'll be split in half again. And another 5 years after that, it'll be split in half again. Okay? Now, what you're looking at here, is an exponential equation, right? Specifically, it would be the equation 100, 0.5 to the power of x over 5, right? And there you can see the amount of radioactive material decreases in an exponential way, because every 5 years you lose half of it. Okay? This is a really important property, by the way. It's how we measure the age of ancient things on Earth, because all living things on Earth contain some radioactive carbon. We breathe it in, but when we die, we stop breathing it in, so the radioactive material in a dead body just decays, right? And it turns out that the radioactive decay of carbon-14, which is a radioactive isotope of carbon, is 5,000 years, 5,740 years, and therefore, even objects that are tens of thousands of years old, we can still figure out roughly how old they are by figuring out how much radioactive carbon they have compared to how much they would have had when they were alive, right? And we can do that because we understand things like this decay curve. So if you've ever wondered when people talk about radiocarbon dating or carbon dating, that's what they mean. They mean they're measuring the amount of radioactive carbon in a fossil or in a substance, and then they're comparing it to what they what they would predict it would have as a living being, right? Compared based on its mass and other things. In any case, this isotope of strontium has a half-life of 25 years, and the half-life process is like the opposite of doubling. It's cutting in half. So whenever you see a half-life, your R is equal to negative 0.5. And again, the reasoning behind that is because you have decay at 50% per period, and therefore R is equal to negative 0.50, right? 50%, and it's negative because it's decay. So anytime you get a half-life question, R is negative 0.5. D is the half-life itself, which is 25 years. T, therefore, has to be measured in years, and NO is whatever we started with, which was 18 milligrams. This means that the amount of material left after X number of years would be equal to that equation right there. And of course, you can make this a little bit simpler if you just do 1 minus 0.5, which of course gives you just 0.5, because it's splitting in half. Okay, and there you go. There's the equation that represents the decay of this strontium. Now it says how much is left after 125 years. So all I would do there is just type in n of 125 and get the answer. So let's go ahead and do that. So it said it was 18 times 0.5, and the half-life was not 5 years, it was 25 years. And you can see that something on a 25-year half-life takes a lot longer than what I drew to decay. But where is it 125 years later? So 125 and f of 125. It's down here at 0.56. So you can see there isn't a great deal of it left 125 years later. Okay? Okay. This one. The population of a town was 24,000 in 1980 and 29,000 in 1990. Determine an exponential equation that models the population of the town t years after 1980. Okay, so t equals years after 1980. Therefore, NO equals the population in 1980, because that's where we started to count from. That's the initial value, right? So NO in our case here is 24,000. Now, what we do not know in this question is R, right? We do not know how the town is growing. We do know that the town grew by 5,000 people during this period, which means we're going to work a little bit differently in this question. We're going to say that n of 10 is equal to 24,000, okay, times 1 plus r to the power of t. I don't think there's any reason to use a d here, because why would we say the town grows at 8% per 3 years? Why don't we just say what it grows at per year, right? We don't need a d, because we could set it ourselves. So we could say 29,000 equals 24,000 times 1 plus r to the t. So we don't know the r here. Well, excuse me, but we do know the t. We do know that the t is 10, because it's 10 years later, right? Okay, so now how do we figure out r? Well, you solve the equation. 29,000, we divide by 24,000. This tells us 1 plus r to the power of 10. I want to get rid of to the power of 10, so how do I get rid of a power? Well, let's do the division first, so we have an answer. The 29,000 divided by 24,000 is 1.21. Okay, let's leave it. Can we leave it as a fraction? 29 over, okay, well, that was dumb. 29 over 24 is the lowest fraction you can get. 1 plus r to the power of 10. Now, how do I cancel out a power of 10? I know you can't answer. I'm just giving you time to think. To cancel out a power of 10, you would take the 10th root. Just like to cancel out a squared, you would take the square root. So what I'm going to do here, okay, 29 over 24, and except I'm going to take the 10th root, okay, and that would be equal to 1 plus r. And the reason being, if you take the 10th root of this side, then the 10th root and the power of 10 cancel. Now, of course, my calculator doesn't have a 10th root button. So how do I find this? Well, I remember that 10th root is the same as to the power of 1 over 10. Right? This and this are the same thing. So now I can go back to my GeoGebra here. I can go a to the power of 1 over 10, and I get the answer. And you want to keep a lot of decimals here, so I'm going to say 1.0191. Oops. Okay, what did I just do? I was able to figure out what r was by taking the 10th root of both sides. Then, of course, I just moved the 1 over, so whatever was left was r. And I see that r is 0.0191. That means the town is growing at 1.91% per year, right? Because 0.0191 is 1.91% when it's written as a percentage as opposed to a decimal. Okay, so determine an exponential equation that models the population of the town. We can do that. We can say the population of the town is equal to 24,000, which was its initial value, 1.0191 to the power of t. And that's it. That will tell you whatever the population is, whatever year in the future you're looking for. Okay. Now, it says use the equation to estimate the population in 2020. So for 2020 is 40 years after 1980. Therefore, t is equal to 40. Therefore, what we want to know is n of 40, which is 24,000, 1.0191 to the power of 40. And n of 40 is equal to, whatever it is. So 24,000, 1 plus b to the power of x, and then g of 40. Oh, right. It's obviously not the right answer. So you see what I did? I put 1 plus 1.0191. I shouldn't have done that because in my question b already has the 1 at the front. So the answer is 51,163 people. Okay, now that's a really good question, by the way. I think there's a good assignment question. It's very similar to that. You should definitely try. Okay, the last one today is a money type of question. an investment one. It says in the year 2000, a sum of $2,000 is invested at a rate of 4% per year for 10 years. What is the growth rate? Okay, so the growth rate is 4%, so therefore r equals 0.04. So we could say 1 plus r in our equation would be 1.04. B, what is the initial amount? The initial amount is NO, and in this case that's $2,000. Okay, C, how many growth periods are there? Well, D is equal to 1 in this question. Therefore, T is equal to number of years and number of growth periods, because we don't have a D value. If we had a D value, right? If we had a D value, T is equal to the number of years, and T over D is equal to the number of growth periods. But since D here is 1, we're not really using it. The number of growth periods is just 1. Now, or it's just T, whatever T is in 10 years. So in this case, so the answer to the question is 10 years and 10 growth periods. By contrast, if you go back up to that strontium question, right? Actually, let me choose this question instead, right? The bacteria was doubling every 15 minutes. How many growth periods were there? There were 4. It doubled 4 times. It grew for 1 hour, but that 1 hour had 4 doubling periods in it, right? In this question, the growth period is just a year. So if it's 10 years, it's 10 growth periods. So there's nothing fancy you need to do there. Okay, write an equation that models the growth of the investment and use it to determine the value after 10 years. Okay, that's easy. NO, every question is the same, right? NO 1 plus r to the power of T over D. Let's fill in what we know. And the value of the investment would be $2,000, 1.04 to the power of T. We don't need a D value, and we know it's growing at 4%, so we just say 1.04 to the T. N of 10, therefore, would be 2,000, 1.04 to the power of 10, and N of 10 is equal to, let's just quickly make a new equation. So 2,000, 1.04 to the power of x, and then f of 10 is $2,960.49. Okay, so the investment $2,960.49 after 10 years. Now, this last part is a important question and is different than anything we've done today. What makes this question different? If you think about the equation that we know, so let's write the equation one more time. Okay, let's analyze for a second. Let's make a different color for different parts and ask what question is asking about which one. Okay, so let's start with N of T. Actually, let's do this in a table. Yeah, 3 items is good. Okay, so item missing, what the question will ask, how to solve. Okay, so let's say in the first case, N of T is missing. We've done a lot with N of T missing today. We've already done a bunch of these ones. If you're looking for N of T, okay, the question is asking how much will there be in the future, at some future date, at some future time. How to solve? Plug in everything into the right side of the equation. We've done this today like 10 times, right? Where we know the equation, we're just plugging into the equation. That's all we have to do if NT is missing. Okay? What if NO is missing? Okay, if NO is missing, the question will be something like, how much was there at the beginning? What you would do there is you would isolate NO by dividing the exponential part under NT. Right? So you'd something like n of t divided by 1 plus r to the power of t over d equals no, right? You just use your algebra to isolate no, right? So if that part's missing, you'll know what to do. It says, what would the question be asking? It would be asking you about how much was there back at the beginning. Okay, if r is missing, okay, which is the one we just did, so if r is missing, the question would say something like, what was the growth rate for the object between NO and NT? So this is like, I'm going to just put here number 6, because what you did in number 6 is what this would be like. What you do here is you isolate R by taking the, t-th root. I should say, oh boy. Okay. Taking the t over d th root, like you did in the question, right? So see number 6. We took the 10th root because it was it was 10 years, right? Now, the last question is the question we're getting now, which is in what year? So it's a question about time. Okay, and these are the hardest ones. So what if they're asking you about t? Okay, you will recognize this question because it will say something like, in what year will the value be double or triple? Like, see what our question's asking? In what year does the investment double? Now, to solve this one, there is an exact way, but it's not part of our curriculum. Exact way to solve this one, you need to guess and check and estimate. Okay? I'll show you the exact way, but I'm not expecting you to know how to do it. So let's show how we would get t in our question. So if t is missing, we should know everything else, right? So it says, in what year does the investment double? So let's write down what we know. Oops. Okay. So n of t is equal to $2,000, 1.04 to the power of t. Now, we know that we don't know what year it is, but we do know that it doubled, right? So we know that 4,000 is equal to 2,000 times 1.04 to the t. Now, if I take the 2,000 and divide it over to the other side, right, I get this equation. Now, this equation is a problem because we do not know a way of solving when an exponent is missing. We don't have a way of doing that yet. As I say, I'm going to show you how to do it, but I'm not expecting you to know how to do it. At this point, what I would be expecting you to do is guess and check. Okay? So let's show what would be a sensible way to guess and check here. Of course, organize yourself. So we're going to make a table. Let's say I want to guess a value, so let's guess t. Like how long will it take the thing to double? Let's say 5 years. I guess that's obviously a bad guess because even 10 years later, I knew it had only gone to $3,000. So let's take a guess that it's 20 years. Okay. So right down here, I'm going to go 1.04 to the power of 20, and what does that equal to? 1.04 to the power of 20 is equal to 2.19. Now, I wanted to know when it's equal to 2. So 2.19 is too big, right? So let's try t equals 15. 1.04 to the power of 15. If I do that, I get 1.8, which is too small. Right? I want it to be equal to 2. It's equal to 1.8. So I'm looking for a number in between these two. Let's say to 17. Let's try 17. 1.04 to the power of 17. Okay, so 1.04 to the power of 17 gives me 1.95. And therefore, so 18, it should be above 2. So let's go 1.04 to the 18. Gives me 2.03. So what I would say as an answer is somewhere between t equals 17 and t equals 18, the investment doubles. Okay? And that would be fine. Really, either answer would be fine. But just so you understand how I'm doing that. Now, this, you can get the exact answer. Okay? To get the exact answer, what you do is you go back to this step. Okay? And as I say, this is extra, so it's not required. But if you want to learn it, I mean, it may help you next year. What you do is you find the button on your calculator that looks like this, log x. Okay? And what you do is you take the log of 2 equals the log of 1.04 to the t, and then you say, so log has this special property where the exponent is allowed to come down into the front, like that. Oh my goodness. 1.0, what just happened? Never seen that before. Okay, the exponent can come down to the front, and then you can get the answer. You do log 2 divided by log 1.04 is equal to t. Now watch what happens when I do that. Log 2 divided by log 1.04 gives me the answer 17.67, which is what we expected. Like, we expected a number between 17 and 18, but now we can get the exact number. 67299. If I take that and plug it into the equation, f of the number g, it gives me 4,000 exactly, like down to 15 decimals, 4,000 exactly, because this is the exact value. So again, if you do it the guess and check way, that's all I'm expecting. If you can get it that way, you'll get full marks. If you're interested in how to get the actual answer, use the log button on your calculator. Take the log of the number you're looking for, and divide it by the log of your base. That will give you the exponent that you need. And this would say the investment doubles 17,67299 years after 1980. Or what it was, 1980, right? So when we started this thing? No, sorry, in the year 2000. Okay? In the year 2000. So the year 2017. Okay? And that's it for today. So remember, every single question has the same equation. And everything about today is about understanding the different parts of this equation. Try the assignment. Okay? Try the textbook homework. Post any questions to the website. Okay?